In a previous lesson, we were looking at constructing sample spaces to determine probabilities. It's great, it was fun, shall I say it was fun, but at the same time, it can be time consuming. For example, if we're drawing 2 cards from a standard 52 card deck with replacement, we're looking at 52 times 52, which equals 2,704 sample points in the sample space. That's a huge sample space. That's a huge tree diagram. That would take me hours to draw that out. So what we're doing in this lesson is we're learning how to solve compound probability problems that contain the word or and without having to construct a sample space. So let's first look at OR problems. The OR probability problems require obtaining a successful outcome for at least one of the given events. This is important. For at least one of the given events. For example, if we were interested in determining the probability of rolling an even number or a number greater than 4. For this situation, rolling either a 2, 4, or 6, which is an even number, or a 5 or a 6, which is a number greater than 4, would be considered successful. So if we rolled a 6, that actually satisfies both criteria, right? 6 is both even and it's bigger than 4. Rolling a 5, I know it's not even, but it's bigger than 4. So that's considered a successful event. So that's what we're looking at. We're looking at OR problems in this lesson. Now, we have a formula for determining the probability of an event, A or B, okay? And this is how we're going to symbolize it. The probability of event A or B occurring is equal to the probability of event A plus the probability of event B minus the probability of A and B, okay? This formula is many times referred to as the addition formula. All right, so let's use it for the following example. So in this problem, it says each of the numbers 1 all the way through 10 is written on a separate piece of paper. The 10 pieces of paper are then placed in a hat, and one piece is randomly selected. Determine the probability that the piece of paper selected contains an even number or a number greater than 6. Consider the following Venn diagram. You can see that in this set here are all the numbers that are even but are not greater than 6. These are the numbers that are odd, so they're not even but they are greater than 6. These are the numbers that are neither even nor greater than 6. These are the numbers here that are both even and greater than 6. Okay, so let's get our formula going. This formula here, the addition formula, okay? So I'm going to get that formula going for us. So I'm going to write it down over here. So here's that addition formula. The probability of us choosing a number that is even or greater than 6 is equal to the probability of it being even plus the probability of it being greater than 6 minus the probability of the selection being even and greater than 6. All right, so let's do the work now. So the probability of it being even. How many numbers total are even between 1 and 10? 5, right? 2, 4, 6, 8, and 10. So 5 out of 10, that's the probability of us selecting a number that is even, plus the probability of choosing a number greater than 6. There are 4 numbers that are greater than 6. 7, 8, 9, and 10. So 4 out of 10 numbers are greater than 6, minus the probability of choosing a number that is both even and greater than 6. So this is one of the reasons for the Venn diagram here, is that it helps us with a visual of there are two numbers that satisfy this description. These two numbers are both even and greater than 6. So therefore, this probability is 2 out of 10. If we do this arithmetic, we'll have the probability of choosing a number that is either even or greater than 6. So then this is 5 plus 4 is 9, minus 2 is 7. So 7/10. So therefore, that's our probability of selecting an even number or a number greater than 6. All right, so this example was illustrating the probability of A or B. So we add the probabilities of A, then the probability of B, minus the probability of A and B, minus the probability of both events occurring simultaneously. Now here's our new example. Consider the same sample space, meaning the numbers 1 through 10, as in the previous example. If one piece of paper is selected, determine the probability that it contains a number less than 5 or a number greater than 8. All right, folks, here's our Venn diagram. Here in set A are all the numbers that are less than 5, so 1, 2, 3, and 4. Here are all the numbers that are greater than 8, 9, and 10. These are the numbers that are neither less than 5 nor greater than 8, 5, 6, 7, or 8. Notice that the intersection of these two sets is empty. There is no number that is less than 5 and greater than 8. That's kind of silly, right? You can't be less than 5 and greater than 8 at the same time. All right, now let's figure out the probability. Let's get our addition formula going. All right, I know it's kind of small, but I was able to fit it all, okay? So the probability, this is what they're asking for, the probability that the number is less than 5 or greater than 8, here's our addition formula. The probability that the number is less than 5 plus the probability that the number is greater than 8 minus the probability that the number is less than 5 and greater than 8, all right? So I'm going to look at my Venn diagram here. All right, the probability that the number is less than 5. So that's all the numbers in that blue circle. There's 4 there. So 4 out of 10 numbers plus the probability that the number is greater than 8. Those are the numbers that are in set B. So that's 2 out of 10 total numbers minus the probability that the number is less than 5 and greater than 8. That's 0. There are no numbers that are less than 5 and greater than 8 at the same time. So then this is 6/10, which simplifies to 3/5. So our conclusion is the probability of selecting a number less than 5 or greater than 8 is 3/5. All right, very good. Let's have a definition of what we mean by mutually exclusive. Before I actually state the definition, I want us to look at this previous example. It is impossible for both of these events to happen simultaneously. It is impossible for a number to be less than 5 and greater than 8 at the same time, right? And so that's why the intersection is empty. And that's what it means to have two events that are mutually exclusive. It means it's impossible for both events to happen at the same time. So this is the definition for mutually exclusive in words. All right. So if two events are mutually exclusive, that means the probability of A and B, a little sloppy there, but B, that's B, this is 0. The probability of both of them happening is 0. That means the addition formula simplifies. That means the addition formula is now like this. If you have two events that are mutually exclusive, then this addition formula, the probability of A or B, simplifies to just this, everybody. P of A plus P of B. You know, usually right after this, we have minus P of A and B, but that's going to be 0. So we don't even bother writing it. So our addition formula is so much simpler when the two events are mutually exclusive. So in this next example, we're talking about a card that is drawn from a standard 52 card deck. And we want to determine whether the following pairs of events are mutually exclusive and then determine the probability of A or B. All right, here are the pairs of events. So the first case is us drawing. One card is drawn, right, from the deck. What's the probability of us choosing a jack or a queen? A jack or a queen. Are these two events mutually exclusive? Yes, they're mutually exclusive because it's impossible to pull one card from the deck and it being a jack and a queen. You can't be both at the same time. So these this pair of events, it is mutually exclusive. For the second one, an ace and a heart. These two events are not mutually exclusive because both of these can happen at the same time. There is an ace of hearts. So you can have event A and B happen at the same time. So these are not mutually exclusive. A red card and a black card. All right, these are mutually exclusive. I think that should be obvious to us. It's impossible to pick one card from the deck and it be red and black, right? That doesn't happen. These are mutually exclusive. A face card, remember a face card means a jack, queen, king, and that's it. And then you have a red card. Now, these are not mutually exclusive because this can happen at the same time. You can pull a jack and it be red. You can pull a king and it be red, right? Because both of these can happen at the same time, so they're not mutually exclusive. All right, folks, just to keep track of which ones are mutually exclusive, I put ME, mutually exclusive, next to these two. These two here are not mutually exclusive. All right, cool. Let's move on. We want to determine the probability of A or B. All right, so these two here, let's talk about the first pair, all right? The probability of A or B. Because these are, I'm looking at the first example, okay, a jack and a queen. Because they are mutually exclusive, this is our formula up here. So it is equal to the probability of A plus the probability of B. All right, so let me move the board up. There we go. All right, so what's the probability of the one card that we draw of it being a jack? Well, how many jacks are there? Well, there's 4 suits, right? There's a diamond, heart, spade, and a club. And so that means there's 4 jacks out of 52, of course, 52 cards. So 4 50-seconds is the probability of that happening. Plus, what's the probability of getting a queen? Well, the same as a jack, right? There's 4 queens. So 4 out of 52. So then this is 8 over 52. And so this simplifies to 2/13. There's our probability of us choosing a jack or a queen. All right, let's handle the next probability. What is the probability of us getting an ace or a heart? All right, these are not mutually exclusive. So we need the full formula here. All right, so we're getting A or B. The formula is the probability of event A happening plus the probability of B happening minus the probability of A and B happening. Okay, so there's our full addition formula. All right, what's the probability of A happening? Remember here in this case is getting an ace. Well, how many aces are there? 4. There's an ace of hearts, an ace of diamonds, ace of clubs, ace of spades. So 4 out of 52. What's the probability of us getting I'm sorry, looking at the wrong one, a heart? Well, remember, there are 4 suits, and so there are 13 cards that have a heart, right? 1 through 10, 1 being an ace, 1 through 10, and then your 3 face cards, Jack, Queen, and King. So the 13 cards that have a heart, right? And so 13 out of 52 minus. What's the probability of getting an ace and a heart? An ace and a heart. Well, there's only one card, an ace of hearts, that is both an ace and a heart, right? So this is minus 1 out of 52. So then this is our formula because these events are not mutually exclusive. All right, so when you do this arithmetic, you get 16 over 52, which is equal to 4 over 13. So there's our probability of getting an ace or a heart. Cool. Let's go for the third one, folks. A probability of us getting a red card or a black card. Now, these are mutually exclusive, so then we have that simpler formula for the addition formula here. And I'm going to move this up if I can. All right, here we go. Here, this is the third one. The probability of A or B, these are mutually exclusive, so it will be simply P of A plus P of B. All right. So in this case, we're talking about the probability of us getting a red card. Now, there are a lot of red cards because you have all of your diamonds are red, and there's 13 of those. And then all of your hearts are red, and there's 13 of those. 13 plus 13. Okay, so there's 26 red cards. Basically, half the deck, right, everybody, is red. So this is 26 over 52, right, which is half, plus I already forgot what B represents here. Oh, a black card. Well, the other half are black, the clubs and the spades. So this is going to be 26 over 52. Now, this is equal to 52 over 52, which is just 1. So a probability of 1 means for sure this event is going to happen. Choosing a random card from this deck, you will for sure get a red card or a black card for sure. Let's go for the last one. A face card or a red card. These are not mutually exclusive, so we need the full formula. All right, let me move this up. All right, here we go. Of course, the full formula says P of A or B is equal to P of A plus P of B minus P of A and B. All right. Okay, the probability of event A happening. And what is event A? I don't remember. There it is. Oops, you know what? That's supposed to be a D. Did anybody catch that? I for sure didn't. So this is example A, B, C, and then this is D. Whatever. All right, a face card. How many face cards do we have? A jack, a queen, a king in each suit. So we have 4 different jacks, 4 different queens, 4 different kings, right? So we have 12 face cards altogether. All right, so then this is 12 over 52 plus, what's event B? A red card. Half of the deck is red. The other half is black, right? So then this is 26 over 52 minus the probability of us having a face card and it being red. How many face cards are red? Well, if there's 12 face cards altogether, half of them are red, half of them are black. And so 6 out of 52. Though that's how many. 6 is the number of face cards that are red. Okay. Anyway, this turns out to be 32 over 52. So this probability here is 8 over 13. Awesome, folks. All right, so we are done for the most part looking at or problems. Now let's look at and problems. When it comes to an and probability problem, we need a favorable outcome in each of the given events, okay? Not just one. Okay. We have this formula for the probability of A and B. It is simply P of A times P of B. Since we must multiply to determine this probability here, this formula is sometimes called the multiplication formula. Now, what's really important is when using the multiplication formula, we always assume that event A has occurred. So this right here has occurred when we're calculating P of B, the probability of event B. All right. So unless we specify otherwise, the probability of A and B indicates that we are determining the probability that event A has occurred and then event B occurs in that order, okay? All right, cool. Let's check out this next example. 2 cards are to be drawn with replacement from a standard 52 card deck. Determine the probability that 2 spades will be selected. All right, how many spades are there in a standard deck? Well, there's 13, right? Ace all the way up through 10, and then the 3 face cards. So there's 13 spades. So when we're talking about 2 events A and B, event A is that we chose a spade, right? And then the second card is a spade as well. All right, so that's what this is. All right, so let's figure out the formula here. So then P of A and B, B, there it is equal to P of, let me change colors here, is equal to P of A times P of B. All right, now, so this is equal to, now what is the probability that the very first card that we choose is a spade? Well, there's 13 spades altogether, right? And then you put that card back. And what's the probability that the second card will be a spade? Well, since you put that card back, there are still 13 spades. So this is the multiplication that needs to occur. So 13 over 52, first of all, is a quarter. It simplifies. So it's easier to do the math if we just simplify. So it's a quarter times a quarter, you know? So it's 1/16. So 1/16 is the probability that we will choose 2 spades. We would choose 2 spades with replacement, okay? Now, this example is exactly the same example, okay? Except we have without replacement, okay? So we have this formula here of P of A and B. And again, event A is that we choose a spade, and event B is that we choose, the other spade as well. You know what I could do? I could rewrite this as the probability that we get 2 spades. How about that? Okay, so then this is going to be equal to the probability of spade number 1. Sorry, that looks sloppy. Times the probability of spade number 2. Now remember that this is without replacement. All right, there are 13 spades, out of 52 cards. But now that you took one of them out, right? So we're assuming that this event happened, right? We're assuming that this event happened. That means there's one less spade now in the deck. So now there's only 12. And there's not 52 cards anymore. There's now only 51 cards because you pulled one out. So then this is a quarter, remember? This simplifies to 4 over 17. So the probability is, well, these 4s cancel, right? Cross cancel. So then the probability is 1/17. All right, cool. Now we define independent events. So two events, A and B, are independent if the occurrence of either event in no way affects the probability of occurrence of the other event. And what's important to note is that when we have an experiment with replacement, that results in independent events. And when you have an experiment without replacement, that results in dependent events. At a fundraiser for a pet shelter, a raffle is held in which 100 tickets are sold. 3 tickets are randomly drawn from a bin without replacement. Okay? And the winners each receive a prize. Are the events of selecting the 3 winners independent? Or it's supposed to say independent or dependent. Let me change that, okay? Now, you do notice that it does say without replacement. And we just finished writing that experiments done without replacement always results in dependent events. So these are dependent events because this is without replacement. Let me explain why these are dependent events. What's the probability for the first drawing of the ticket from the bin? Okay, there's 100 tickets, so the probability is that you would win is 1 over 100, right? Your ticket out of 100 tickets that are sold. All right, let's say they did not pick your ticket. Now they're going for the second ticket. Now, they did not put that first ticket that they pulled, they didn't put it back. It's without replacement. So what's the probability that they choose your ticket the second time, assuming you didn't win the first time? Well, 1 out of, watch this, 99. See, the probability changed because now there's 1 less ticket in the bin. Let's say you didn't win in the second drawing either. So your ticket is still in the bin. Now for the third drawing, what's your chances or your probability of winning? 1 out of what? 98, right? My point is the probability has changed and it will continue to change each time they draw a ticket because these are without replacement. In other words, these are dependent events. So that's our answer there, okay? All right, here's our last example, all right? A medical research study on a new medicine for arthritis is being conducted with 25 patients. After the study was concluded, it was determined that 19 patients reacted favorably to the medicine, 2 reacted unfavorably, and 4 were unaffected. If 3 of the patients are randomly selected, determine the probability of each of the following. All right, let's go through each one separately. The first one is all 3 reacted favorably. Okay, so one thing to keep in mind, each time a patient is selected, the number of patients remaining decreases by 1. Okay, so just keep that in mind. So for the first one, all 3 reacted favorably. All right, so here's our probability formula. All right, so here we go. So the probability that the first patient acted or reacted favorably is going to be 19, right? They told us that 19 out of 25 times, 19 patients reacted favorably. Now, they have chosen one patient already. So now there's not 25 anymore, there's 24. So when they select the second patient, there's now 24 total, no longer 25. And now there's not 19 patients that reacted favorably because you've chosen one of them already. So we're assuming that this happened, right? This event occurred, that we have selected a patient at random, and that patient has reacted favorably. So that means there's no longer 19, but now there's 18 times. Now, for the third patient to react favorably, now there's 17, right? And there's 23 total patients altogether. Okay? So these are definitely dependent events. When you multiply straight across, you get 969 over 2300. This is the probability that all three patients that were selected at random, all three reacted favorably to the medicine. Okay, let's go for the next one now, which is the first patient reacted, not reactive. Okay, I changed it. Reacted favorably. The second patient reacted unfavorably, and the third patient was unaffected. All right, so let me move up here. If I can't, there we go. All right, so let's do this. So here we go. So we're looking at the probability that the first one that we select reacted favorably. All right, so we know that 19 reacted favorably out of 25 times. Now, we already selected a patient. That means there's only 24 patients left. Okay, now how many of them reacted unfavorably? Well, it said 2 times. Now there's only 23 patients left in the pool to choose from, and we want to know unaffected. Now for the unaffected, it told us that there were 4 that were unaffected. So this product is 19, after you simplify, of course, over 1,725. Remember, you don't have to multiply straight across. You can cross cancel a lot to help you. All right, cool. Like 4 goes into 24 6 times, and then 2 goes into 24. 2 goes into 6 3 times. So both 2 and 4 can divide into 24. But anyway, you can multiply straight across and then simplify, which I think is more challenging. But at the end of the day, this is the probability. Let's go for the next one. No patient reacted. Sorry about the typos. Reacted favorably. All right, so let me move up even more. All right, here we go. So we're selecting 3 patients, and we want to know what the probability that none of them reacted favorably. Okay, let's be careful with the language here. It did say find the probability, I can scroll back up, that no patient reacted favorably. Now hold on just a second. If you did not react favorably, that means you either were unaffected or you reacted unfavorably. So if you did not react favorably, that means you were either unaffected or you reacted unfavorably. And in this problem, there, right here, 4 were unaffected. 2 reacted unfavorably. So that means 2 plus 4, 6 out of the 25 did not react favorably. 6 out of the 25. So I just want us to be careful about pulling the right numbers there. So 6 out of 25, all right, times, now there's only 24 patients to select from and 5 that did not react favorably. Now for the third selection, there's only 23 patients left and 4 patients out of that many that did not react favorably. This probability is 1 over 115. All right, very good. All right, so for the last one, I believe at least one patient reacted favorably. Now, for this one, I think we can use the formula that we learned in an earlier lesson. Here, let me write it down for us. So we learned this formula that the probability of an event happening at least once is equal to 1 minus the probability of the event that the event does not happen at all. Now, we just figured out that the probability that none reacted favorably is 1 over 115. We want to know now in part D, the last part, is the probability of at least one. See, at least once, at least one of the 3 patients reacted favorably. I believe that's what they asked us for. Yes, right there in part D, at least one patient reacted favorably. So the way I can do this then is I can use what we found earlier. So then this is going to be 1 minus the probability that none of the 3 patients reacted favorably, right? So 1 over 115. So then this is, don't forget that 1 whole is 115 over 115. All right. So then this is 114 over 115. This is very close to 1. So the probability of this happening is very, 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 very high. Meaning, if you're choosing 3 patients at random, it is very likely that at least one of them reacted favorably to the medicine.